Welcome to the top 10 list of cool kernel debugging tricks by Code Machine. My name is T. Roy and I'm going to be a presenter. If you're an engineer working on Windows driver development and debugging, or you're a security researcher working on Windows kernel mode rootkits, this presentation is for you. In fact, if you have anything to do with the Windows kernel, you'll find this presentation informative and useful. In this presentation, we're going to go over some of the nifty tricks that will help you become more effective when debugging or researching the Windows kernel. To get maximum value from this presentation, you're expected to be familiar with kernel debugger setup, debugging symbols, and some basic kernel debugger commands. Here is a quick introduction to Code Machine. We are a consulting and training company focused on security research and development on Windows, Linux, Android, and embedded systems. We teach classroom-based training courses with hands-on labs to companies all over the world. We also offer open enrollment courses to the public in the Washington, D.C. metro area in the U.S. Students from more than 50 countries have attended our courses and have always given us stellar feedback and reviews, some of which is available on our Facebook page and website. This presentation is going to be full of demos, so it is important to spend a few minutes to understand the environment that we will be using to show the demos, so that you can replicate this environment on your own systems if you desire. On the host system, I'm running the 64-bit version of Windows 8.1. Microsoft Hyper-V is the virtualization software which is built into enterprise and higher SKUs of Windows 8 and later versions of Windows. In Hyper-V, the guest OS is 64-bit version of Windows 8.1. The guest OS has been configured for kernel debugging over serial port using the boot configuration editor bcdedit. Hyper-V has been set up to map the guest VM serial port to a name pipe on the host which the kernel debugger connects to. The kernel debugger is WinDBG version 6.3.9600. WinDBG is a part of the debugging tools for Windows package which is installed on the host system. The old Windows 7 SP1 Windows Driver Kit or WDK is used to build a driver and load it on the target Windows 8.1 guest OS. With that background, let's take a look at some cool kernel debugging tricks. This trick is going to be of interest to you if you're developing or debugging hardware drivers for Windows. During driver development, it is frequently necessary to find out whether a specific device has been enumerated or detected on the system. Dev nodes or device node data structures are software representation of hardware devices that are maintained by the kernel mode component of the Windows plug-and-play manager. All hardware devices in the system are organized in a hierarchy called the device tree or dev node tree as shown on the slide. The nodes of this tree fall into two categories. There are leaf nodes that represent devices that don't enumerate or host other devices, like a USB mouse, a Bluetooth headset, or a PCI network adapter. And then there are devices that do enumerate child devices. Such devices are called buses, like ACPI, PCI, USB, and IDE. These devices form the non-leaf nodes of the device tree. If a hardware device is enumerated successfully, the system creates the corresponding dev node structure and adds it to the appropriate place in the device tree. The kernel debugger's bang dev node command can be used to display a specific dev node in this device tree. Running the command bang devnode 0, 1 displays the entire device tree starting at the root. Let's run that command in the kernel debugger. Let's take a quick look at the output of this command. In this output, we have PCI ID devices like disk drives, we also have ACPI devices like CPUs as well as the ACPI fixed button. This list contains every single device that has been found inside the Hyper-V virtual machine and can be used to find out if the device of interest has been found or not. So in general, this is a very, very useful command. WinDBG not only has a very powerful command set that lets us perform all kinds of debugging tasks, but it also supports a very powerful scripting language letting us automate these tasks. Script files are simple text files that contain a set of debugger commands that can be executed without any user intervention once the script is fired off. While covering all facets of the debugger scripting language is out of scope of this presentation, we will take a look at some of the key features of the debugger scripting language using the example that automates the retrieval of all process callbacks that have been installed in the system by various drivers. Kernel mode process callbacks are functions installed by kernel modules that are invoked whenever any process is created or terminated in the system, and it's used as a process creation and deletion notification mechanism by a lot of different security software. In this example, we're going to look at debugger registers, pseudo registers, aliases, control blocks, MASM operators, and the C++ expression evaluator. Before we jump into the actual script, let's try to understand a little bit more about process callbacks. When a driver registers a process callback, the pointer to the callback function is stored in an internal data structure, and an array of pointers to such data structures is maintained in the global variable ps create process notify routine. Depending on the API that was used to register the process callbacks, either one of the two counters, PSP create process notify routine exCount or PSP create process notify routine count, is incremented when a new callback is registered in the system. In the debugger script, we compute the count of the total number of callbacks and then iterate through the array of pointers to get the respective structures and display the symbol associated with the callback function pointer. Now let's go over the script. Throughout the script, T0 to T6 are the debugger temporary registers and are used as variables, and the debugger's register or R command is used when referencing them for the first time in a new line on the script. In lines 5 and 6, DWO is the MASM operator that is used to read the D-word or 32-bit values stored in the respective counter variables. In line number 8, we are setting up the alias count to be the sum of temporary registers T0 and T1. In line 9, .printf is a control flow token and a part of the debugger scripting language which can be used to format and display values from the debugger script. In line number 10, the .for is also a control flow token. In line number 12, the poi is a MASM operator similar to DWO but is used to reference pointer size values, and PDR size is a pseudo register that is automatically set to 4 or 8 depending on whether the target system being debugged is a 32-bit or 64-bit system respectively. In line number 13, in order for the debugger to process the ampersand and the tilde operators, both of which belong to C++ language, we have to switch to the C++ expression evaluator using AT C++. And in line number 17, we delete the alias value count so that it does not interfere with the subsequent executions of the script. Now that we understand the script, let's see how we can run it in the debugger. One way to force the debugger to read an external file and interpret the contents as debugger commands is the $greater than less than command. Let's run that command in WinDBG to load the script file psnotify.wdb. The script output shows the list of process creation callbacks. And that list is here. Here are the symbols associated with the callbacks, and here are the respective function pointers. We will now take a more detailed look at something we saw briefly in the last trick, which is the debugger's built-in C++ expression evaluator. The question mark command can be used during debugging to evaluate any C++ expression. This command supports full C++ expression syntax, including accessing fields of structures and unions, referencing array elements, typecasting pointers to data structures, as well as accessing bit fields. As a simple example of the usage of this command, let's try to find out the size of the kernel data structure called eProcess. The size of operator is used in C++ to compute the size of any structure. We will use this operator along with the question mark command to find the size of the eProcess structure in the Windows kernel. Now let's look at a more elaborate example in which we convert a global variable from a symbol to an address, typecast the pointer to a structure type, access a field of the structure using that pointer, and then read the contents of an array element using the structure. We start with a global variable called PS_initial_system_process, which is the address of the eProcess structure for the system process and belongs to the module NTOS kernel, or NT in short. In order to evaluate this symbol and convert it to an address, we use the debugger's built-in MASM expression evaluator, add_masm. Once we have the address, we typecast it to the eProcess structure type in NTOS kernel. After this, we use the typecasted pointer to access the PCB field of the eProcess structure. And then finally, we access the first element, which is element at index 0 in the ideal node array within PCB. And we evaluate this whole expression using the question mark command. A very common task when debugging a system with a kernel debugger is to set breakpoints on user mode functions. We want those breakpoints to trigger only when a function is called by a specific process, as opposed to being called by any process running on the system. Since the kernel debugger has visibility into the whole system, including all processes that are running on the system, when setting a breakpoint on a user mode address, we need to be in the right process context for the breakpoint to trigger as desired. When we break into the system using a kernel debugger, the current process context from the debugger's perspective is whichever process happened to be executing on the CPU at the time when the debugger broke in. This is not necessarily the process that we want to set the breakpoint in. For example, as shown on the slide, process 1 may be the current process that the debugger initially breaks into, but we might want to set a breakpoint on a user mode address in process number 3. In this case, we have to instruct the kernel debugger to switch to the context of process 3 before setting any user mode breakpoints. This can be achieved using the .process command. Let's first find out the current process context using the kernel debugger as we break into the virtual machine. As far as the kernel debugger is concerned, the system process is the current process. Let's say we want to set a breakpoint only when Notepad calls the Win32 API create file. In order to do that, we need to first find the pointer to the eProcess data structure for Notepad. Here is the eProcess data structure for the executable notepad.exe. eProcess is the name of the structure that Windows kernel maintains internally for each and every process that is running on the system. Now we need to tell the kernel debugger to switch us to the process context of Notepad using the eProcess pointer that we just found. Now we let the target system run and wait for the debugger to get into the right process context of Notepad. We get a break in the kernel debugger. Let's find out what process context we are actually in this time. Now that we're in the right process context, we force the debugger to load all the user mode symbols for this process. And now we should be able to set breakpoints on the wide char version of the Win32 API create file using the BP command. We let the virtual machine run. We switch to the virtual machine and ask Notepad to open a file for us. And as soon as we do that, the breakpoint triggers in the kernel debugger. Now we can continue our normal debugging activities, like, for example, looking at the call stack. From the call stack, we can see that we have indeed broken into the white-jar version of create file in the DLL kernel32. And if we try to find out what process context you're in, we see that we broke only when Notepad called that function. This trick applies to debugging dynamic memory allocation problems like memory leaks, double freeze, as well as memory corruption. Let's go over some basics. Pools are regions in the kernel or system virtual address space from where drivers and the kernel itself allocates memory at runtime. User mode applications have access to functions like malloc or new to allocate memory. However, in the kernel, the way to allocate memory dynamically is using the function xAllocatePoolWidthTag and freed using the function xFreePoolWidthTag. Both these functions take a 4-character tag that is used to identify the kernel module or even the function within the module that allocated the memory. This is extremely useful when debugging, since the pool tag can be used for attribution or module identification. When live debugging kernel mode allocation problems, it is not uncommon to want to break when a specific data structure is being allocated or freed. Setting breakpoints on xAllocatePoolWidthTag or xFreePoolWidthTag turn out to be not very useful, since a breakpoint will trigger every single time any component in the system attempts to allocate or free memory. A much better way to achieve this goal is to make use of the wonderful feature in the Windows kernel, which is a variable called poolHitTag. PoolHitTag is a global variable in the kernel whose value can be set to any 4-character pool tag, and both xAllocatePoolWidthTag and xFreePoolWidthTag will trigger a breakpoint in the debugger when the pool tag passed to these functions match the one in poolHitTag. This is just like setting a conditional breakpoint without the performance problems and system slowdown issues typically associated with conditional breakpoints in frequently used functions in the kernel. Let's examine the current value of poolHitTag in the debugger. Let's set poolHitTag to the pool tag associated with file objects, which is the 4-character sequence FILE. When setting the value in poolHitTag, we must reverse it because of little endian memory layout on Windows. Let's make sure it is set as expected. Now let's run the system and wait for the pool tag to trigger our breakpoint. The breakpoint triggers. Let's examine the call stack to find out who is attempting to perform this pool allocation. So from the call stack, it seems like an application is trying to query file attributes, and that is resulting in the file object being allocated using xAllocatePoolWidthTag. WinDBG commands display their output in a specific format. Oftentimes, we need to perform further processing on the raw output of a command to extract the data that we need. A simple but cumbersome way to perform processing on the output of a debugger command is to save the output of a command to a file, run an external test processing utility on that file, and then examine their output. WinDBG has a built-in feature that makes it very convenient to do this directly without ever leaving the debugger environment. This is achieved by the .shell command, which allows us to run external executables on the raw output of the debugger commands and then get the results back in the debugger for examination. In this example that we'll use to demonstrate this, we would like to learn more about the threads in the process lsas.exe. We want to know what each thread in the process lsas is waiting for. To obtain a list of all the threads in the process lsas, we run the kernel debugger command bang process 07 lsas.exe. We then take the output of the command and send it using the .shell command to an external process outside the debugger, findstr, which is a built-in executable in Windows, and then get the output of the command back in the debugger. When we run this command, it will filter everything out except the wait statements that we see here in the output of the threads displayed by the bang process 07 command. In the output of the .shell command, we see only the information that we asked for. The rest of the command output was filtered by findstr. The ability to use good old Unix command-like tools like awk, sed, grep, cut, sort can be very useful in extracting the information we need from the WinDBG commands. If you're a driver developer who has gone through the build, deploy, test, debug cycle day in and day out, this trick will bring you significant time savings. During the driver development process, blue screens and system hangs occur very frequently. And when that happens, the steps that you follow are to debug the problem, fix the problem in your driver, build the driver, and then deploy the new driver to the target system for another round of testing. The problem here is that the target system had crashed or hung with your old driver, and that old driver is still present on the target system, which will result in a crash or hang again, especially if the driver is set to load automatically. So the question is, how do you break this continuous crash cycle and get your new bug fix driver onto the target system? The debugger has a wonderful built-in command to help you with this step, and that is the kdfiles command. The fundamental idea behind kdfiles is that the kernel debugger already uses a connection between the host system on which your new driver is available and the target system on which your new driver must be copied. So why not use the same connection to transfer the driver binary from the host to the target system? The kdfiles command needs two pieces of information: path on the host system where the new driver binary has been created. This would be the build output directory, and the path on the target system where the old driver binary is present that needs to be replaced. Let's run the command to automatically transfer the driver module driver.sys from the build directory on the host to the Windows System32 drivers directory on the target. It is important to understand that the driver.sys is already installed as a service on the target system, and an older version of the driver binary is already present in the C Windows System 32 drivers directory. Once the KD file's driver mapping is specified, whenever an attempt is made to load the old driver binary on the target system, it sends a notification to the debugger running on the host, which responds by sending the new driver binary over to the target using the debugger transport, which in our case is a serial connection. And the target system then loads a new driver instead of the old one. Here we can see that as soon as we attempt to load the driver in the guest OS, the debugger running on the host received a notification and transferred the driver over the serial connection to the target system. Oftentimes, when you're trying to debug memory corruption issues, you'll have the need to associate a pool tag or some such string found in a data structure or on the stack with a specific module in the system. In order to do this, you need a means to quickly search through all the kernel modules loaded in memory for the presence of the desired string. WinDBG provides a couple of commands that can be combined together to achieve this goal. The bang for each module command iterates through all the modules that are loaded on the system. The s-a command searches for the specified ASCII string through the given memory range. We combine the two commands to iterate through all the modules loaded in the kernel virtual address space and search for the pool tag ntfx that we picked at random from the base to the end of every single module. The bang for each module command replaces the aliases @base and @end with the actual base and end memory addresses of the modules as it iterates through each one of them. This command quickly scans the modules for the pool tag and lists all the addresses where it found a match. We can now pick any of the addresses and run the list near or ln command to not only find the name of the module, but also the function that it's using with this pool tag. The list near command tells us that the module that contains this pool tag is NTFS. And one of the functions within NTFS that uses this tag is NTFS FCB non-page index lookaside list. When analyzing malware and rootkits, it becomes necessary to detect if any operating system binaries in memory have been tampered with. Tampering includes hooking functions in modules as well as patching instructions in memory after modules have been loaded. Kernel security mitigations like PatchGuard make it hard but not impossible to patch or hook operating system binaries in the kernel. One way to detect if a specific Windows binary is patched is for the debugger to compare the in-memory image of the binary with the on-disk image of the binary, and the debugger's bang check image command does exactly this. When a module is loaded in memory, the debugger has access to the name of the module as well as the build timestamp and the size of the module. The debugger is able to use this information and download the original copy of the binary from Microsoft's public symbol server that hosts not just the symbols but also the executable images for every single binary that ships with Windows. Once the debugger is able to download the binary, it can compare that with the in-memory image to detect tampering. Since we want to check all the modules in the system for corruption, intentionally or accidental, we will use the iterator bang for each module and run the bang check image on every single module that bang for each module finds. As we have seen before, the alias @module name is replaced by the actual name of the module as bang for each module iterates through it. If any module were to have a corruption, this command would display the address of the corruption as well as the actual bytes that were corrupted. Linked lists are used extensively by the Windows kernel as well as in most reasonably complex drivers. The basic construct used to create doubly linked lists in Windows is the list underscore entry structure, which contains two fields, a forward link or F link and the backward link or B link. The F link field points to the next list entry structure in the linked list, and the B link points to the previous list entry structure in the linked list. A typical usage of the list entry structure is to encapsulate it in a larger structure or a container structure, and then use it to link multiple container structures together to form the list. In this example we're going to look at, we want to display the list of all the kernel modules that are loaded on the system. For every kernel module, there is a loader data table entry structure that contains information about the module, including its name and entry point. In this structure, there is a field called in_load_order_links, which is of type list entry that is used to link multiple loader data table entry structures together. The anchor, or the head of this list, is stored in a global variable called PS loaded module list, which is also of type list entry. If we are able to walk through this list in the debugger, we should be able to display a list of all the kernel modules that are loaded on the system. Let's see how we can do that. The debugger command displayType or DT displays the contents of structures. The DT command takes the flag -L, which causes DT to not just display one structure, but all the structures that are part of the list. The DT command requires a starting point, for which we use the flink field of the PS loaded module list. We can access the contents of this field, which would be the pointer to the first node of the list, using the poi operator. Then we specify the container structure type, which in our case is loader data table entry. Next, we specify the field that DD has to follow to traverse to the next node in the list, which in our case is in load order links.flink. And finally, we specify the fields that we want the DD command to display for every node that it encounters in the list. What DD displays is the list of all the modules along with their entry point addresses. And that concludes this presentation. We hope you enjoyed it. If you want to learn more about the Windows kernel, please take a look at our training courses. We can schedule private delivery of these courses at your company, or you can sign up for our open enrollment classes. We look forward to seeing you in our classes. Thanks for watching this Code Machine presentation.